brought to you by Thomas Allgaier and Franis. This edition highlights key LinkedIn posts on electrification and battery technology in weeks 14 and 15. Franis is a B2B market research company that supports automotive suppliers with building feature-by-feature competitive intelligence that shows exactly how their product stacks up against the competition. You can find more info in the description.
Yeah, and welcome everyone to this deep dive. We are super excited to have you with us as we unpack some of the biggest trends in electrification and battery tech that have been blowing up across LinkedIn recently.
Exactly. And to kick things off, I want you to imagine something. Imagine buying a $2,000 television, right? You bring it home and you mount it to your living room wall using a flimsy $2 plastic bracket.
Oh, that sounds like a disaster waiting to happen.
Right, because you're trusting this massive, highly technical investment to the absolute weakest link. And, well, looking closely at the mobility industry discussions over the past 2 weeks, that is exactly what's happening with electric vehicle infrastructure.
Yeah, it really is.
The bill is finally coming due. I mean, we are officially past the honeymoon phase of just, deploying hardware.
Yeah.
Now we are slamming straight into the gritty operational realities of making this tech actually work.
The conversation has absolutely pivoted. It's gone from celebration to system optimization. The era of just getting steel in the ground is completely over.
Totally.
Over calendar weeks 14 and 15, the top voices in the space were entirely focused on operational uptime, the actual economics of these charging sites, severe grid bottlenecks, and of course, the geopolitical realities of battery supply chains.
So let's start right at the physical connection point, the charger itself. James Tillman brought up this phenomenon that he calls the cheap hardware trap in public charging.
Oh yeah, that was a great post.
He points out that taking the lowest bid on a DC fast charger almost guarantees that your project will just bleed capital in the long run.
Because it's a textbook false economy.
Right.
Tillman mapped out the cascading failures that happen when you buy unsupported hardware. And it isn't just about the machine breaking later on. The chaos actually starts during construction.
Really? Like before it's even turned on?
Exactly. Project managers and EPCs, the engineering, procurement, and construction teams, they often receive these cheap chargers with poorly translated installation manuals. Or, honestly, sometimes no manual at all.
Wait, walk me through the mechanics of that on a job site. If you're an EPC pouring concrete, how does a bad manual actually cost you money?
Well, it forces the engineering teams to make assumptions. They have to guess based on generic spec sheets.
Ooh, no.
Right. So they'll trench the site, lay down the conduit, pull all this expensive copper wire, and pour a concrete pad based on those generic plans. Then the actual charger arrives, and the mounting holes don't align with the concrete anchors.
You're kidding.
I wish I was. Or worse, the internal terminal blocks require a totally different gauge of wire than what was pulled underground. So you end up having to tear up fresh concrete, resize the wiring, and suddenly your cheap hardware has triggered this massive multi-week standoff.
Between the vendor, the installer, and the site operator, that is a nightmare.
Yep.
And what blows my mind is that even after all that chaotic installation, the equipment rarely functions seamlessly anyway. Like Kate Kudoli shared a study covering Finland, Germany, and the UK, and it revealed that nearly 40% of public charging sessions still experience issues.
40%. It's wild.
It is a massive friction point. We're talking slow charging, payment failures, and this is the worst connectors getting physically locked to the car. How is the failure rate still sitting at 40%?
A huge portion of that comes down to what Paul Raj identified as handshake glitches.
Handshake glitches.
Yeah. So when you plug a vehicle into a high-speed charger, power doesn't just instantly flow, right? The car and the charger have this highly complex millisecond-level conversation.
Right, they have to sync up.
Exactly. The car's software says, hey, I need 400 volts at this specific amperage. And the charger has to verify it can deliver exactly that before the heavy physical metal contactors inside the machine actually snap shut.
So if there's even like a microscopic timing error in that software negotiation,
the system panics. If the timing protocol is off by even a fraction of a second, the safety systems trigger an abort to prevent an arc flash or a battery surge.
Wow.
So the contactors stay open, the screen throws some vague error code, and the driver is just left stranded.
Which brings up a huge point. If operators are treating these chargers like passive infrastructure, like a park bench you just bolt down and forget about, instead of active software-dependent retail spaces, the economics are going to completely destroy them.
Without a doubt.
Bodin Rohalia posted some numbers on this. He noted the average public charger in the U.S. operates at just 6 to 10% utilization.
You cannot build a sustainable business model on heavy capital assets that sit idle 90% of the day. You just can't. And even during the 10% of the time they are utilized, the margin conversion is absolutely brutal.
Let's get into those margins, because Tomas Gabor broke down the math using Fasten's operational numbers. And it perfectly illustrates the financial squeeze here.
It really does.
So Gabor mentioned they make about 53 cents per kilowatt hour in gross profit at the plug, which honestly sounds incredibly healthy. Why is that misleading?
Because gross profit completely ignores the reality of running a network.
Right.
You have to bridge that 53 cents down to EBITDA.
Right. The company's operating profit before accountants factor in taxes, interest, and depreciation.
Exactly. So first, you strip away the site lease costs, the grid connection fees, and daily maintenance. That 53 cents drops to roughly 24 cents.
Okay. Still something. But then you have the corporate layer on top of that.
Precisely. Once you factor in the broader company overhead, the software backend licensing, the expansion teams, and crucially, the massive depreciation on these really expensive hardware assets, that 53-cent gross profit at the plug shrinks to just 5 cents.
5 cents per kilowatt hour.
Yes. Only a tenth of the gross margin actually survives down to the underlying company EBITDA level.
That is razor thin. And that 5-cent margin can be completely wiped out by someone with a pair of bolt cutters.
Oh, the copper theft, yeah.
Syed Haseeb Hassan brought this up. There is this wild, asymmetric reality operators are facing. Thieves are cutting these thick, liquid-cooled charging cables in the middle of the night for, maybe 50 to 100 euros in scrap copper value.
Is that? Yeah.
But the operator is hit with a 1,500 to 3,500 euro bill just for new cable, plus the specialized labor to install it. It is easily 4,000 euros in replacement costs.
And you lose out on your thin 5-cent margins for weeks while you wait for a service team. It completely exposes how financially fragile a single public passenger charger can be.
Exactly. So, and this is where it gets really interesting. If a single passenger charger is this fraught, what happens when a logistics operator tries to scale this for a commercial fleet of heavy-duty trucks? Because, you clearly cannot just copy-paste the public passenger model into heavy transport.
You absolutely can't. The first hard truth about fleet electrification, which was brought up by Jared Archer, is that electric trucks should not be deployed everywhere right now.
Right.
The industry needs to stop pretending an electric semi is a one-to-one drop-in replacement for a diesel semi on every single route.
Yeah, Marina Machnock backed this up with a brilliant operational point. She noted that if fleets take the time to fundamentally re-optimize their logistics routing, specifically for the range and payload characteristics of electric trucks.
Rather than just blindly forcing them onto old diesel routes.
Exactly. If they re-optimize, they can literally double their electrification rates and cost savings.
Yeah.
But it requires completely rethinking the hub-and-spoke logistics model.
But here's the catch. Rethinking the routes doesn't solve the charging access problem. Johannes Matthews highlighted this staggering statistic. Out of roughly 30,000 heavy-duty DC fast chargers currently shipped into the European market, 21,000 of them are locked behind private depot fences. Imagine
if 70% of the world's diesel pumps were locked behind a company's private fence. The supply chain would grind to a halt.
It would be chaos. 70% of the heavy-duty infrastructure in Europe is essentially invisible and inaccessible to any truck that doesn't belong to that specific yard.
But wait, break that down for me. If the hardware is already sitting there, fully powered up, connected to the grid, why can't a third-party truck just pull in, tap a credit card, and charge? Are these companies hoarding capacity out of range anxiety, or is the software just failing to share it safely?
It's the software. It lacks what Matthews calls an Airbnb-like software layer. It is not just about processing a payment, right? If a depot owner lets a third-party truck plug in, they need absolute software certainty that the visiting truck won't draw so much peak power that the depot's own buses fail to charge by morning.
Oh, that makes sense.
Yeah, the software has to manage dynamic load balancing, route scheduling, and site access all at once. Without that predictive energy management layer, depot owners basically hoard their capacity out of operational self-defense.
Wow. That makes the logistics of shared infrastructure incredibly difficult. And, when fleets do attempt to build public shared hubs, the sheer scale of the engineering is wild.
Huge.
Gelberg Rodriguez, Seneth Apat, and Thomas Laurent discuss EV Realty's massive new 9-megawatt truck charging hub out in San Bernardino, California.
9 megawatts is an industrial scale footprint. And what's really fascinating about that EV Realty project, as Rodriguez shared, is that they were actively trenching, laying conduit, and doing civil engineering with their OEM partner Kempower, while the actual technology standards were still being drafted.
Right, because they are preparing for the megawatt charging system, or MCS, which isn't even fully finalized yet. We aren't just talking about bigger cables here.
No, not at all.
MCS involves massive new pin configurations, intense active liquid cooling systems designed to push over 1,000 amps of current continuously. Building the civil infrastructure for that without finalized cut sheets or locked-in wiring schematics, that requires an intense level of risk management.
It really highlights a severe talent gap in this space. The mobility industry doesn't just need venture capital right now. It needs highly specialized engineering teams capable of delivering complex, high-voltage infrastructure under conditions of extreme regulatory and technical uncertainty.
So let's say EV Realty manages to navigate this wild west of unfinalized hardware. They actually build this 9-megawatt hub. What happens when they call the local utility and ask them to just, turn it on? Because you can buy the trucks, you can build the chargers, but the physical electrical grid is rapidly becoming the ultimate choke point here.
Oh, the grid simply was not built for this kind of localized, dense power draw. Victoria Hutton provided a highly effective mental model to visualize the strain. She points out that 1 megawatt of power is roughly equivalent to 500 electric kettles boiling water simultaneously.
Okay, so EV Realty's 9-megawatt hub is 4,500 kettles firing up at the exact same moment.
Exactly. And Hutton points out that a single 20-megawatt transit bus depot is 10,000 kettles.
That's insane.
Think of a local distribution grid like a finely tuned string quartet, right? It hums along, managing a few residential neighborhoods, keeping the acoustic frequency perfectly balanced. Dropping a massive heavy-duty depot onto that local substation is like dropping a stadium rock band right into the middle of the quartet.
The quartet doesn't stand a chance.
Exactly. The voltage drops, the frequency violently distorts, and the local transformers physically overheat.
Denis Leskovar painted a very stark picture of this reality. He looked at a standard highway in Slovenia with kilometers of heavy trucks backed up in transit. And he did the math. If you transition those vehicles, each truck needs around 500 kilowatt hours of energy, potentially twice a day.
That's massive.
To charge just a fraction of them overnight in a localized area requires grid upgrades that take 2 to 5 years to permit and build.
The traditional utility grid just cannot scale fast enough. This is exactly why the conversation is shifting toward decentralized edge-of-grid solutions. Skip Bowman brought up a massive shift happening in Australia right now.
Oh, distributed storage, right?
Yeah. In just the past year, Australian households and parked EVs have added an estimated 10 to 14 gigawatt hours of distributed battery storage.
Which is incredible, considering Australia's entire grid-scale utility battery fleet is only sitting at about 5 to 8 gigawatt hours. The distributed, privately owned assets are vastly outpacing the massive utility projects.
By a factor of 2. And Robert Farago noted how critical this distributed fleet is becoming. Australia produces so much solar energy in the middle of the day that power prices go negative and utility-scale solar has to be curtailed, basically thrown away.
Right.
A fleet of EVs with bidirectional charging capabilities could absorb all that excess daytime solar and stabilize the grid.
But hold on, this brings us straight into the vehicle-to-grid debate, or V2G. Mark Kay refers to V2G as the, quote, missing layer of the European energy stack. He envisions 140 million parked EVs acting as a giant virtual power plant.
It sounds great on paper.
It does. But looking at the technical experts over the last 2 weeks, Andreas Heinrich, Arne Slovak, and Mark Mulden, they are pouring ice water on this hype.
And rightfully so, because the underlying mechanism of V2G is incredibly complex. As Mark Multum explains, the moment a vehicle feeds power back into the grid, it is no longer just a consumer appliance. It becomes a heavily regulated grid generator. It must strictly obey local grid codes.
Wait, how does a car actually act as a grid generator? Like, why is it different from just draining a battery into your house?
Because the wider grid operates on alternating current at a very specific frequency. If a local power plant trips offline and the grid frequency microdips, the car has to instantly detect that and push reactive power back to stabilize the local frequency.
Oh, wow.
Orchestrating that requires a flawless, multi-layered software protocol stack. You're using standards like ISO 150 11820 for the car-to-charger communication and OCPP 2.1 for the charger-to-utility communication.
And according to Arne Schloak, who runs a testing facility for these systems, the industry is failing at the basics right now. He shared that basic smart charging functions like just waking an EV up from a scheduled pause are currently failing. I mean, if we're currently seeing a 40% issue rate with basic one-way public charging, aren't we getting way ahead of ourselves asking the car to negotiate complex grid codes and pump power back?
We really are.
It's like trying to teach a kid calculus when they were still failing basic addition.
That is exactly the operational concern Andreas Heinrich raised. We are trying to add massive bidirectional software complexity to a hardware ecosystem that is still deeply struggling with basic interoperability.
Yeah.
Until the lower-level communication layers are absolutely bulletproof, V2G is going to remain trapped in small-scale pilot programs. The car must charge reliably every single time before it can be a power plant.
So let's step back and look at the bigger picture here. We have EPCs tearing up concrete due to bad manuals. We have 40% failure rates on public chargers. Copper thieves are destroying margins. 21,000 depot chargers are locked behind private fences due to missing software.
It's a lot.
The grid requires 5-year upgrades, and the communication protocols are failing basic addition. With all of this massive systemic friction, why is the mobility industry still pushing so hard?
Because macroeconomics and geopolitics are leaving them zero alternatives. The fragility of our current fossil energy logistics system is on full display. Mika Smola highlighted how recent conflicts in the Middle East caused immediate violent spikes in global diesel prices.
Right.
He noted the missiles hadn't even finished falling before diesel costs started climbing.
And logistics operators running on razor-thin margins simply cannot absorb a sudden doubling of their fuel inputs.
Exactly. Simola pointed to the transit system in Helsinki, which stopped buying diesel buses back in 2019. It wasn't driven by environmental altruism, it was pure, brutal arithmetic.
The math just makes sense.
Yeah. A diesel bus in their fleet costs roughly 80 euros per 100 kilometers to operate. An electric bus costs about 10 euros per 100 kilometers.
That is an 8x operational difference. I mean, when the financial math is that stark, you figure out how to make the infrastructure work, regardless of the headaches. Roger Atkins pointed out that the tipping point for EV adoption has officially shifted from ecological ambition to pure financial necessity. The internal combustion status quo is just becoming too expensive to maintain.
However, escaping dependency on imported fossil fuels brings up a completely different geopolitical bottleneck.
The batteries.
Yes. Nemanja Mikic provided a crucial reality check regarding the battery supply chain. European operators desperately want battery independence from China, but Mikic highlights that over 98% of the world's LFP cathode material lithium iron phosphate, which is the heavy, durable, cheap chemistry perfect for commercial fleets, and up to 98% of synthetic graphite used in battery anodes, is produced in China.
Wow. So you can't just flip a switch, declare independence, and build a localized supply chain overnight.
No, you really can't innovate your way out of a 90% material dependency in one move. Mikic outlined a very strict, sequenced 3-step plan that Europe must follow if it actually wants to build local capacity without destroying quality control.
Okay, let's unpack that plan. So basically, do we have to copy the recipe exactly as it's written before we try swapping out the ingredients?
That is exactly it. Step 1. Europe must start producing cells locally, but they must use Chinese raw materials, Chinese factory equipment, and Chinese manufacturing processes. You do not change a single variable until you prove you can hold quality at massive production volumes.
Makes sense.
Step 2, you invite those Chinese material suppliers to build their material processing plants locally in Europe. Step 3, only after that local ecosystem is completely stable do you slowly requalify those operations into European-run facilities through technology transfers.
It is entirely about quality control then.
Exactly. If you try to change the anode materials, the cell design, the factory equipment, and the manufacturing process all at the exact same time, and the battery fails testing, you have no idea which of those 4 variables caused the failure.
Right. You need a known good baseline.
Pretending the European mobility sector doesn't depend heavily on China right now is only costing companies time and massive amounts of capital.
It really underscores how deeply intertwined every layer of this transition is. I mean, you solve the vehicle cost by moving to LFP batteries, But then you hit a charging infrastructure bottleneck, you solve the chargers. You hit a massive utility grid bottleneck, you solve the grid by attempting VDG, and you hit a software protocol failure. And overarching all of it is a geopolitical supply chain reality.
It is, without question, the ultimate systems engineering problem of our generation.
Absolutely. Well, if you enjoyed this episode, new episodes drop every 2 weeks. Also check out our other editions on future mobility and market evolution, next-gen vehicle intelligence, and commercial fleet insights. Thank you so much for joining us on this deep dive. Don't forget to subscribe so you never miss an edition.
And I just want to leave you with one final thought to mull over. We've talked about hardware traps, software protocols, lock depots, and grid strain today. If a mobility operator's total cost of ownership now depends entirely on utility grid access and software communication protocols, does the mobility industry need to stop thinking of itself as purely building vehicles and start realizing it is now fundamentally in the energy and data routing business?